Welcome everyone to today's lecture about quantum chaos, part of our weekly lecture series on quantum chaos. So today it's my great pleasure to introduce the speaker, Silvia Pappalardi. Silvia is currently finishing her PhD at CISA and ICTP in Italy, where she started in 2016 after getting her degree in theoretical physics from the Sapienza University of Rome. In her research, she considers subjects like entanglement in quantum ecodynamics, long-range models, and semi-classical approaches. And today she will be talking to us about entanglement dynamics and chaos in systems with collective and long-range interactions. As usual, everyone can just ask questions at the chat in YouTube, and we'll put them to the speaker. And at the end of the talk, there will also be time to ask additional questions. So, Silvia, it's over to you.
Okay. Thanks a lot, Peter and Pablo, for asking me to give this presentation. I'm very honored to be part of this series on quantum chaos. And as Peter said, I'm going to talk about the dynamics of entanglement in systems which have long range or collective interactions. So this presentation will be based on joint work with Alessio Le Rose, who is now a postdoc in Geneva in the group of Dima Banin. And it's based on two papers. The first one was aiming at understanding the origin of the counterintuitive slow growth of entanglement entropy in systems with long-range interaction, which have been recognized in several numerical works. While the second one provides a unifying framework for the understanding of entanglement in systems with semi-classical behavior. But since the latter somehow is the underlying mechanism for the former, I'm going first to talk about systems with collective interaction, and then show you how to apply the same ideas to fully many-body systems, which anyhow are not too far from their classical limit. But I'm first going to start with an introduction, which won't be too precise, but I'm going to go back on the definitions more and more details in the main part of the talk. Okay, but first let me start very away from the classical limit, more in the spirit of the previous talks in this series, in a full regime. So let me set h bar equal to 1. And describe a little bit the setting in which one is interested in. So typically, when studying out of equilibrium dynamics of quantum system, one starts from a pure quantum state, which can be the ground state of a given Hamiltonian, or a low entangled state, like in this cartoon, a separable state in which one can identify by partition between two sets A and B, two subspaces A and B. And then typically the system is let evolve unitarily through the unitary evolution identified by Hamiltonian H. And what we know is that in the presence of interaction, the system will undergo to a non-trivial dynamics, and observables will evolve non-trivially, and quantum correlation will grow non-locally. So a possible way to quantify such non-local growth of correlation is through the study of the entanglement entropy dynamics. So the entanglement entropy is defined as the von Neumann entropy of the reduced density matrix rho A of T, where what we're doing is we are tracing away the factor, the complement B from the full quantum pure state, and then we compute the entanglement entropy. Now, for systems with short-range interaction, there is a well-set paradigm describing the growth of this quantity out of equilibrium. So for thermalizing systems and also for integrable system, the entanglement entropy typically grows in time linearly and saturates to a value which is proportional to the volume of the partition. This behavior has been explained, for example, in the case of integrable systems, through the beautiful quasi-particle picture of Calabrese and Cardi, in which entanglement is understood as the integration of quasi-particles generated at the same point, which arrives in A and B simultaneously. On the other hand, the presence of conserved or quasi-conserved quantities causes a dramatic slowdown of the entanglement growth, which corresponds to a saturation in the absence of interactions, or to the characteristic logarithmic growth in the case of many-body localization. Now, this first cartoon shows you how important, how insightful entanglement dynamics is in the study of many-body dynamics. And also there is another aspect which is quite relevant, that entanglement dynamics somehow sets a bound on our ability to simulate the classical complex dynamics on quantum dynamics on classical devices, since TDVT, the MRG techniques, all the MPS techniques are somehow bounded by the growth of the entanglement entropy. So the question that one asks is what happens when a system is characterized by a classical limit. So I take the completely opposite limit, in which h bar is a small parameter which can go to 0. And what is well known is that if the system is initialized in a coherent wave packet, which is Gaussian and it's narrow, in the sense that its variance scales like h bar, then observables obey classical equation of motion as dictated by the standard Hamilton equation, at least at small time. So this is in the spirit of the Ehrenfest theorem. So for small time, I mean before a long time scale, after which interference effect will enter into the game. And I'm going to be more precise on this later. So the natural question is how to reconcile entanglement, which is the characteristic trait of quantum mechanics, with such a semi-classical behavior. And this question is obviously not new, but has been asked and discussed, I would say, since for a long time. And one of the first insights came by Paz and Durek in this series of papers at the beginning of the 90s. And they were interested in the coherence in open systems, and they described the growth of the entanglement between the system and the environment as the growth of the initial Wigner function describing the subsystem into an hyperdimensional hyperpancake, which I'm describing here pictorially. And then they also understood that the entropy will be given by the logarithm of the volume of this hyperpancake. Furthermore, in the presence of chaos, this growth increases linearly in time with a rate given by the sum of the positive Lyapunov exponents. This conjecture somehow has been confirmed numerically, analytically at the end of the 90s and at the beginning of the 2000s by a large body of papers. Since in those years, as you know, that the topic of quantum chaos was very lively and active, but somehow the community was focused on different concepts, the one that we're focused on now. Indeed, they were interested in the coherence, irreversibility, and they were mainly studying observables like the Loschmidt echo or the purity decay. As I mentioned, somehow their interest on entanglement dynamics has gained a renewed attention also now, so motivated also by the first slide. And this renewed attention has spread over different communities and has really an interdisciplinary character. So it ranges from quantum information, out of equilibrium, statistical mechanics, condensed matter, also to high energy physics. And in this last context, the Durek and Pax conjecture a couple of years ago has been put on solid grounds by Bianchi and collaborators, but I'm also going to go back on this. Now, I would say that one of the reasons why this topic has gained so much attention also more recently is definitely due to the technological advances in the field of ultra-cold atom physics, which has allowed for probing time scales which were completely impossible to probe before. Now, interestingly, many atomic platforms from Bose-Einstein and condensates, cavity QD, or different kind of trackyons, indeed are described by a collective uniform interaction between their constituents, which allows for a semi-classical treatment of their dynamics. Therefore, such systems offer somehow a natural playground for the understanding of the entanglement dynamics with collective interactions. So what I also want to mention is that contemporary quote marks, so modern studies on entanglement dynamics focus on different concepts to respect to the Loschmidt or the purity decay. And the more paradigmatic, the more celebrated one is definitely the bipartite entanglement that we already introduced. So the von Neumann entanglement entropy, and also older sisters, the Renyi entropies, which are a family of entropies. This is just the second Renyi entropy, which is the minus the logarithm of the trace of rho a square. Another way to characterize the entanglement of a system is through its multipartite entanglement, which somehow answers to a complementary question, which is rather how many spins are entangled, what are the blocks of entangled spins, and this is answered by the quantum Fisher information, and this quantity, which was actually introduced in quantum optics in metrology, is such that if I take its density, so this Fisher information for the state rho and a given operator O, if its density is bigger than M, then there are at least M+1 parties that are entangled. So I have to compute it, and that gives me the size of the biggest entangled block. Unfortunately, for time constraint, I cannot go into the details of the derivation because it's a very different setting. But in the case of pure state, its definition is very simple, and the Fisher information is just given by the fourth time the variance of an operator O. As you can see, as you can imagine, different operators lead different bounds, and one would in principle want to maximize the quantum Fisher information in order to give the best estimate of the entanglement content on the state. Now, recently, the study of chaos has received a renewed attention with emphasis of the new notion of scrambling. New or not new, I don't know. So this concept, a possible way to characterize scrambling is through the square commutator, which is the expectation value of the square of a commutator between an observable at time t and an observable at time 0. If you expand this commutator, you find that there are those out-of-time ordered correlators, or OTOC, which are correlators with an unusual time ordering. So these are definitely new objects. Now, this object was actually introduced back in 1969 by Lyapunov Chinnikov, that we're considering a semiclassical limit of a superconducting system, but was definitely made popular by the famous talk of Kitaev at KITP in 2015, which has motivated, I would say, an incredible study, a new study of scrambling, with emphasis on different notions. So, for example, we heard last time about information scrambling, there is operator scrambling, and different kind of notions. In this talk, I will focus rather on the classical limit of this out-of-time ordered correlator. Now, the natural question that one can ask is whether these concepts are related, or at least they are related in simple systems, so in systems which can be described semi-classically. So this is the question that we ask, and somehow we provide an answer. So, okay, now let me be a little bit more precise with the setting that I want to consider. So I'm taking a semi-classical model in the sense that we will have a small parameter, effective h bar, which we will send to 0. And now my system has a small n degrees of freedom, and which is described by 2n conjugate variables obeying the standard commutational relations. And the effective h bar is somehow defined by the Hamiltonian, which can be rescaled in this way. And this immediately gives the Heisenberg equation of motion for the operator. So this is the quantum equation of motion. Then one can equivalently somehow define the classical system with on phase space characterized by the 2n conjugate variables, which obey the standard Poisson brackets, and their evolution is given by the classical Hamilton-Jacobi equation. Now, if I start from a system, from a state whose fluctuations, which are pictorially represented by this gray area, scale like square root of the effective Planck constant, then I can identify the expectation value of the operator at time t with the classical trajectory, with the classical observables, at least at the leading order. And this approximation holds until I can treat the dynamics, until I can treat the state as a Gaussian wave packet. Therefore, this defines somehow the Ehrenfest time scale as the time scale for which the wave packet is non-Gaussian, and somehow the variance is of the order of the system size. And after this, quantum effects enter into the place, and non-classical dynamics occurs. Now, this is not just an abstract construction, but it describes the dynamics of quantum systems with fully connected Hamiltonians, which through permutational symmetry allow an exact mapping to quantum models with few degrees of freedom. So let me consider an example of what I'm saying, which is given by infinite range spin systems. Now, this Hamiltonian is nothing but a generic spin model with arbitrary all-to-all p-body interaction between their individual spins. This can be even just an mean field Ising Hamiltonian with transverse field. So that is the prototypical example. And notice here the rescaling n to the power p, where n is the number of spins, which is here in order to ensure the extensivity of the energy. Now, this Hamiltonian can be easily be rewritten in terms of the collective spin, which is the sum over all the sides of the individual spins. And this rescaling allows us to identify the effective Planck constant, which scales like 1 over the system size. So in this class of systems, the thermodynamic limit coincides with the classical limit. Now, for these models, the total spin is extensive and conserved, and ground states maxima lie in the subsector of the maximal spin. Therefore, the typical quench dynamics, in which I start from a ground state and then I change one parameter of the Hamiltonian, will keep my quantum state in this small subsector of the whole Hilbert space, which scales like with the system size. So in the limit n equals to infinity, again, I can apply somehow the ideas outlined in the previous slide. So I can picture the classical variable, which is the expectation value over the system size, as a point on this big block sphere, and also its dynamics will occur in this phase space with the classical equations. But now, if I want to study quantum dynamics, I have to include quantum fluctuations, which in general will have a non-trivial evolution. This is really the essence of quantum mechanics somehow. And in general, these quantum fluctuations that start being small, they will get squeezed, and I will go back on this even later. So they will grow non-trivially during the evolution up to a point in which the size of these quantum fluctuations will be of the order of the system size. And again, we hit the Ehrenfest time. Just let me mention that this is much more general. So the same treatment can be applied to systems that have permutational symmetry, or to composite systems in which I couple this infinite range system to other degrees of freedom, like a cavity mode, or two sets of infinite range systems, like two kick-top or things like this. Okay, now before going to the study of the quantum dynamics, which is the essence, I just want to do a little interlude on classical chaos. So as we know, deterministic chaos is characterized by the strong sensitivity of the dynamics of the change of initial conditions. So the typical thing is to start from an initial condition, consider an infinitesimal displacement, and study the dynamics of the distance between the two, which in the case of underlying chaos grows exponentially with a rate given by the maximal Lyapunov exponent. To be more precise, this Lyapunov exponent depends on time and on the initial condition. So what one does is to take the limit for the infinitesimal displacement and to time going to infinity. This is important. But this number, lambda, doesn't exhaust all the possible information that are encoded in the flow. So a way to characterize it is to consider an infinitesimal hypercube which surrounds the initial condition. It's identified by these infinitesimal displacements which span the tangent space. And what the evolution will do will move this point in time along the trajectory and will deform the hypercube. Now, in order to study how the hypercube is deformed, one basically derives the variational equation, which is the linearization of the infinitesimal displacements around the classical trajectory, where we have the classical linear stability matrix, and this admits a formal solution, which is given, so the displacement, the infinitesimal displacement at time t is given by the evolutor, which is the t exponent of the integral, etc., times the initial condition. So this is the formal solution also in classical mechanics. Now, the deformation of the hypercube is captured by the following matrix, the Ozeledet matrix, which is the symmetrization basically of the evolutor of the dynamics. The eigenvalues of this matrix are contained in the definition of the Lyapunov spectrum, which is defined as the limit of t going to infinity of 1 over t, the logarithm of the square root of these eigenvalues. And you can convince yourself that the maximum of this corresponds exactly to this definition that I gave before. Now, the existence of such limit is the content of the celebrated Ozeledet multiplicative theorem, which gives the name to this matrix. The maximum of the spectrum is the maximum Lyapunov exponent. But also, knowing the spectrum, we can also access the Kolmogorov-Sinai entropy, which was also present in the Zurek impact conjecture, which is an important quantifier of dynamical chaos and related to the asymptotic loss of information induced by arbitrary coarse graining, finer and finer coarse graining of the information. And by the Bayesian relation is given by the sum of the positive Lyapunov exponents. So somehow, the Ozeledet matrix encodes all the chaotic information that one would wish to find about the classical flow. Okay, now we can go back to the dynamics of quantum fluctuations, which we define as the distance between the operator and the classical trajectory, which at the leading order corresponds to the average. And the rescaling here is such that these quantum fluctuations are order 1. And notice that they also describe the fluctuations around the instantaneous spin direction in the case of fully connected systems. Also at generic time t. And this can be shown, for example, by the use of time-dependent Holstein-Primakov transformation. Now, in order to find how these quantum fluctuations evolve in time, what we do is that we put them back in the Hamiltonian, and then we solve the time-dependent problem by keeping only the quadratic terms. So at this level, basically what we're doing is that we are linearizing the dynamics close to the classical trajectory. And indeed, the dynamics of the quantum fluctuations is linearized, and it's described exactly by the same variational equation that I introduced before. So as you see, in this case, I'm describing the growth of quantum fluctuation on a state, but they have exactly the same identical solution. But notice that now, before the RMFS time, somehow the system is treated within a Gaussian approximation. So all the informations are encoded in the correlation matrix, which is defined in this way. It's just the symmetrized correlation matrix between the quantum fluctuations, which, because of the formal solution, turns out to be identical to the Ozeledet matrix of the classical limit. So just to summarize what we're doing so far, we're considering systems with a classical limit where at the leading order, the expectation value of time t is given by the classical one. And what I showed you is that quantum fluctuations also evolve like the infinitesimal displacements around the classical solution. And furthermore, all the information on the system before the RMFS time is given by the matrix which encodes the Lyapunov spectrum. Okay, what is even more interesting is that this matrix can be related to all the quantifiers of chaos that I introduced before. So let me start from the entanglement entropy. And first of all, I need to define a bipartition, because typically one studies systems with short-range interactions where the natural partition are spatial ones between two regions of space. In this case, instead, we have permutational symmetry, so that would be meaningless. Instead, we consider the entanglement between two sets of spins, in the case of spin systems. So we consider NA spins and a block of NB spins. Or in the case of composite systems, like for example, the Dicke model, which describes the interaction between N spins to a cavity mode. In this case, the natural bipartition is between the spins and the cavity. Okay. So once we have a bipartition, all the entanglement is given basically by the reduced correlation matrix, which is the full correlation matrix, but reduced only to degrees of freedom of the subsystem. And this is what Bianchi, Hackle, and collaborators showed, that any entropy is exactly given by the logarithm of twice the determinant, which is really the logarithm of the volume of the reduced subsystem, exactly what's stated by Patz and Zurek concerning the hyperpancake. Furthermore, the entanglement entropy goes asymptotically in this way. So somehow this gives a first connection between the entanglement and the entanglement entropy and the correlation matrix G of T. Also, the other quantifiers can be related in this way. So the quantum Fisher information, which you remember was the variance of some quantum, the variance of some operator in this setting is the maximum transverse fluctuation. So it's just 4 times the maximum eigenvalue. One can also relate that to squeezing. So spin squeezing is another very important quantifiers in quantum optics and quantum information. It's related to the deformation of quantum fluctuation in a direction, specific direction. So in this case, it's the minimum of the eigenvalue. And also the square commutator can be treated on equal footing, and one can derive at the leading order that the square commutator is related to the matrix elements of the evolutor. Now I just want to mention that this expression become even much nicer in the case of a fully connected spin system or the Dicke model, in which one can consider a bipartition with only 1 degree of freedom. Okay. Also, what is important here is that this connection holds time by time. So even at time equal to 0, this is true. Okay. Now, these relations, from this relation, it follows that all the quantifiers of chaos will be dictated by the classical trajectory. And the dynamics will be given depending on the nature of the orbit. So first of all, the dynamics of GDT is determined by the regularity properties of the system. So in the case of stable configuration, where for example, the trajectory doesn't move, or harmonic oscillator, the quantum fluctuation, this matrix simply, the elements of this matrix simply oscillate in time. Of integrable systems, or KM tori, in which small integrability breaking do not perturb the integrable tori. Nearby trajectories at most separate linearly in time for most of the trajectories, and therefore this quantity at most grow like t square. And on the other hand, in the case of chaotic systems or also on unstable trajectories, this quantity is dominated by the maximum Lyapunov exponent. So this allows to predict the behavior of the entanglement quantifiers also in all these cases, and also the way the Ehrenfest time scales. So, for example, in the integrable case, the entanglement entropy will grow logarithmically in time, while the Fisher information and the square commutator will grow polynomially in time, before the Ehrenfest time, which scales like the inverse, the square root of the inverse of the effective Planck constant, like square root of n in the case of spin systems. In the chaotic case, on the other hand, the entanglement entropy is proportional to the Kolmogorov-Sinai entropy, while the square commutator and the Fisher information grow exponentially with the maximum one. So first of all, notice this difference. The entanglement entropy is sensible to all the spectrum, while these other quantifiers are not. But in this case, the Ehrenfest time is definitely smaller, and it's only logarithmically big in n. And then otherwise, everything is just oscillatory. Now, notice that these predictions are true for the asymptotic, so the one that I'm putting here for infinite times, while by studying entanglement in time, I probe the finite time Lyapunov exponent in general. Okay, now let me briefly exemplify these findings on two paradigmatic models of quantum chaos. So let me start from the kick-top, which cannot. Okay, let me start from the kick-top, which describes a global spin S, which is periodically kicked in time with kicking strength proportional to its magnetization along the Z direction. And upon increasing the kicking strength, one can have a transition from an integrable region, a regular region, up to a chaotic region. So this is the stroboscopic map. Now, what we want to do, we want to check whether the analytical treatment, which is correct in the thermodynamic limit, is in agreement with the exact diagonalization results. So we start from initial states, which are the one represented here by this black dot, corresponding to different kind of orbits, and then we compare the exact evolution with the one that we can do for the analytical with the analytical machinery. In this case, one can also write exact maps, since this model is particularly simple. And I just want to show you the two more extreme cases. So in the case of regular trajectory, you see here in black is it's the result for the infinite n limit, in which I see a clear logarithmic growth, and here a clear t square. While for finite n, the results go on top of the analytic one, but saturate when they hit the Ehrenfest time scale, which can be showed by rescaling is exactly square root of n. On the other hand, in the presence of chaos, the growth of the entanglement is only linear in time, while the square commutator and the official information grow exponentially fast. Now, you can notice here that there is a dotted line, a dashed line, which corresponds to the value of the exact Lyapunov exponent, which is the one defined with the infinite limit. So this is calculated using the standard techniques, for example, of Benettin et al., Galgani from the 80s. And you see that there is a difference, small but difference between the behavior of this object and the initial time growth, even though the analytical results predicts the early time growth. Okay, so this is an example of a driven system of one dimensions. Let me now go very briefly on an example of Hamiltonian chaos, in which I have 2 degrees of freedom. So upon changing energy or parameters, I can induce a chaotic behavior. And indeed, those are 3 examples for 3 classes of parameter of systems characterized by regular orbit, mixed phase space, or fully chaotic one. This is the Poincaré map. And as I mentioned, describes the interaction between n spins and a bosonic mode. This is also very relevant experimentally. So I do the same thing. I compare the exact quantum dynamics compared numerically with the semiclassical machinery. And now let me show you what happens for this mixed phase space. And again, in the case of the integrable trajectory, the regular tori, I see this clear logarithmic growth, and by increasing system size, I go more and more on top of the analytic prediction. And this is the same also for the chaotic case. But notice here that there is an even bigger difference between the slope given by the finite time results and the true Lyapunov exponent. But this is also predicted because it's widely known that for Hamiltonian chaos, Lyapunov exponents converge at larger times. Okay, but let me conclude this first part by telling that one can interpret these results in an appealing and experimentally natural way, following from the fact that we have seen that the main result of Bianchi et al. Essentially, is that the entanglement entropy is given by the logarithm of the reduced volume, which grows in time while the global volume is conserved because of unitary evolution. So this means, so for example, in the case of isolated spin systems, I can see the growth of entanglement as induced by the spin squeezing. Indeed, the area of the shaded gray fluctuations remains conserved, but because of interaction, this induces spin squeezing, which makes entanglement accumulating between A and B. On the other hand, in systems which are composite, the global volume is conserved, but if I look at the volume of the reduced spin system, I will see the area of the volume increasing in time. So this really, somehow we can read the entanglement growing really by measuring the volume of the reduced spin state. Okay. So in the time that I have left, I want to show you that somehow now at the collective level, everything seems quite clear. But more interesting and difficult problem is what happens when interactions have some structure. So when alpha, describing the range of interaction, is not zero, but it's finite. And what we will see is that the notorious quasi-particle picture basically gets suppressed, while the relevant mechanism is exactly the spin squeezing that I described you before. So let me just start sketching a little bit what are long-range systems, which are systems whose interaction is described by an algebraically decaying function of the distance between the two, with an exponent alpha, which is zero in the case of uniform collective interaction, and can be tuned to be bigger or smaller than the dimensionality. We focus on systems where alpha is smaller than dimensionality, so those are truly long-range systems, and they've been studied a lot classically, as they give rise to very interesting physics that doesn't have classical counterparts, but also in quantum dynamics are now even subject of a great attention, also in this case, because they can be realized in experiments. And this Hamiltonian that you see here actually engineered on trapped ions platforms, which are one of the most promising platforms of quantum computation. So in different labs worldwide, they can tune the parameter alpha depending on the specific arrangement that they have on the atom ions. Now, what one would think regarding entanglement entropy is that since degrees of freedom which are distant can get correlated immediately because of the range of interaction, one would expect entanglement to grow very fast. Instead, somehow it was surprising the result that Andrew Daly and collaborators found back in 2013, in which they showed that, on the other hand, when alpha was smaller than the dimensionality, entanglement was growing only logarithmically in time. And they said this is much smaller than the growth of their short-range counterpart, which you remember is linear from the first slide. So somehow we wish to understand why this is the case. So let's go back to our treatment. So how do we approach the problem? First of all, notice that with respect to the previous slide, here I'm rescaling the interaction through this Katz normalization, which is here again to ensure the extensivity of the Hamiltonian. Out of equilibrium, you can see it as putting it here in such a way to have the two energy scales to be comparable. And in the case of alpha equal to 0, this is just the usual n of the mean field calculations. Okay, now how we approach this model is that we show that the quasi-particle contribution gets suppressed. In order to show that, and I'm going to be very brief, but if you want, we can discuss about that more, we basically expand in quantum fluctuations again around the classical solution. Now, the classical solution is the one that, of course, for the collective mode, for the uniform mode at k equal to 0. But in principle, one can perform also Primakov transformations on the individual spin and at finite wavelength k, and obtain an Hamiltonian which is a sum of two terms. So the first term, H0, is the classical collective Hamiltonian, which is integrable, and it's integrable somehow with two meanings. So it's integrable because its classical limit is the infinite range spin system that I described before, and being only 1 degree of freedom, since the energy is conserved, it can only be integrable, meaning that generically the trajectories will be regular. But it's integrable also from more a quantum perspective, since one can identify a set of conserved quantities, which are the occupation numbers of the spin waves at finite k. And their density, we call it the spin wave, the number of spin waves in the system is exactly equal to 0, only when we have alpha equal to 0. And then by putting alpha different from 0, we in principle break
reminder,
integrability.
you've been talking for about 40 minutes.
Okay, thank you, Peter. So in this case, we break integrability because this other Hamiltonian in principle will excite quasi-particles, spin waves at all wavelengths, generating a non-trivial dynamics of this number of collective excitations. Anyhow, it turns out that these spin waves are quasi-conserved and are not that important during the dynamics. And this is due to the specific analytical structure of the decoupling of the interaction with the spin waves. So this is the Fourier transform. So let me show you why. Basically, we study the Fourier transform of the interaction. This is an example for a one-dimensional model. So you see that for alpha very big, in which we would retrieve the short range limit. So for alpha equal to infinity, we have nearest neighbor interaction. And in this case, this is smooth and should be a cosinus. But for alpha smaller than dimensionality, this becomes very peaked around 0. Furthermore, by increasing system size, we see that this approaches more or less a delta function. Now, one can perform a better estimate of the Fourier transform of the interaction of the coupling to the spin waves, and see and derive the following bound, which says that basically for any finite k, in the thermodynamic limit, the spin waves are suppressed and they're not excited during the dynamics. This in principle implies that there is a long pre-thermalization time scale before which the spin waves are not excited at all, and the system basically just remains trapped around this small submanifold of the full Hilbert space, even though integrability is broken. So there is this quasi-conservation of spin waves in analogy with the pre-thermalization discussed by Mori in the same context. So one can in principle also refine this analysis and zoom at small wavelength where k scales like 1/n. And in this case, this spin wave might break permutational invariance. So one can think that they can induce some strange effect on the dynamics of the model. So in order to treat them, what one can do is to perform a stability analysis. So basically the Hamiltonian that we wrote is done in this way. We have the infinite range part plus a discrete set, because we only have a few spin wave excitations that might break permutational symmetry, that are driven in time. So this is essentially a set of harmonic periodic oscillators, which can exhibit different dynamics depending on the drive. And notice that the drive here is given by the big precession of the global spin on the Bloch sphere. So in principle, they might destroy our classical dynamics, but it turns out that most of them are stable. So let me show another phase, another block sphere, which here basically black means stable, while colored means this purple means unstable. And this shows that for basically all the initial conditions at given parameters, these spin waves will only be stable, small periodic oscillations on top of the classical solution. Anyhow, it also shows that close to the classical separatrix, there might open finite regions where there are somehow unstable spin waves excitations. This is somehow a second order of treatment of this analysis. Indeed, all these analysis can be checked comparing with numerics. Basically, what we're saying is that the contribution of the spin waves is suppressed, and the quasi-particle picture is suppressed, and one expects the leading order to be the classical one. But since the classical one is the integrable limit, in this case, we expect a logarithmic growth of entanglement, which is indeed what was found by the experiment. And so this is indeed our comparison, in which we compare the black line is the analytical treatment that one can perform. And in blue, with increasing system size, we performed TDVT, which is time-dependent variational principle on the MPS subspace, which is the state-of-the-art technique to study long-range dynamics. And you see that for alpha very small, the dynamics goes exactly on top of the analytical one. And this is the case also for relatively big alpha. So here in black, you see basically the dynamics of the classical limit. And you see that by increasing system size, the results, even for relatively small system sizes, go on top of the black solution. In this case, also in the inset, there is somehow a more, let me zoom, there is somehow a more refined analysis. So in gray, there is only the classical contribution, which is what I explained in the first part of the talk, while one can also include the contribution of the finite spin waves generated by the dynamics, but since they are conserved, they are just oscillating, and this is just an oscillating bounded contribution on top of the logarithmic growth. So this basically explains why the entanglement entropy is dictated by this counterintuitive log. Okay, so I think I'm right on time. Let me conclude. Let me summarize. So first of all, we somehow show and we saw a general approach which allows to connect different kind of entanglement in semiclassical systems, and this is basically a very different mechanism to the one that has been studied in the fully quantum systems, where entanglement is usually induced by the propagation or the suppression of conserved quantities. So this new mechanism, somehow it's very interesting experimentally, because spin squeezing, for example, is it's an relatively easy quantity to access experimentally, and also it has important consequences for quantum information, since all these concepts seemingly are related, they turn out to be related. And also somehow we have seen that this is the mechanism underlying the case of long-range systems, in which there is this new picture of in presence of a dominant zero mode, where the usual quasi-particle contribution instead is suppressed. So this also somehow it's one of the consequences is that it explains why long-range systems, even if they break integrability, somehow are represent an instance of ergodicity breaking because they remain very close to their classical limit. This still needs to be understood, whether it's an effect that holds over even in the thermodynamic limit. And also somehow this small growth of entanglement underlies the efficiency of these methods, of semi-classical methods for systems with long-range interactions. There is a big number of open questions, of things that could be interesting to study. For example, study also open systems to characterize entanglement negativity, or use these techniques to study this new kind of semi-classical analysis that now are even more relevant based on TDVP approaches, where it has been found that for several quenches, even there, surprisingly, entanglement remains extremely small. So this could be applied. And then another open, more difficult question is what happens after the Ehrenfest time, where we have seen numerically that that everything saturates. And I'm sure you also will have many other questions. And I thank everyone for being here and listening to me.
Thank you, Silvia. Very nice talk. That was great. Let's move on to the questions. So we have one right now. We have a bit of a lag, so I'll just remember everyone that they can post questions on the YouTube chat. And we'll start with one by Manuel Munoz. He asks, in the second part, if one wants to avoid the long pre-thermalization time, how should the Hamiltonian be modified other than changing the interaction range?
So if one wants to avoid, meaning go directly to after the pre-thermalization regime. So what I would say is that in the thermodynamic limit, this pre-thermalization regime is here, provided that the spin waves contribution is suppressed. So in principle, if we are in a region of the parameters where the spin waves are just stable, in the thermodynamic limit, there is no way to avoid this pre-thermalization time, which will go to infinity. So we will only have this semi-classical logarithmic growth. On the other hand, a way to avoid that is to focus on these critical quenches or quasi-critical quenches, I don't know. That I'm sorry that I didn't explain well because we didn't have much time. So these are situations for which the individual spin waves, even if they don't interact within each other, they can explode in time. So their dynamics can be very big. And this is a phenomenon that is remnant to parametric resonance. So in this case, the treatment, our analytical treatment breaks down. So this pre-thermalization time scale somehow ceases to be valid because this other contribution becomes the dominant one at a much shorter time scale. So I don't know if this answers that.
Okay, thank you. I actually have one that's related to that, which is, so in this same slide, the H0 corresponds to alpha equals 0, right? Okay, so I guess this is kind of a general question. I mean, I would expect that, if I have these spin systems, right? If I have, for example, a chain with short range interactions, something like MPS can be used to kind of efficiently solve the dynamics for that, if I'm interested in dynamics. If I have alpha, corresponding to infinite range, I have these collective spin systems which are, starting, they conserve the total spin number, so you can kind of solve them efficiently too. Do you expect that, is there some value of alpha? One of the things that you were showing is that for a small alpha, right, the solution kind of revolves around the semi-classical solution. So do you expect that for some value of alpha, the system will be like the hardest to simulate? Or something like that?
In question. So first of all, I'm not sure if I understood that for small for big alpha, so in the short range case, I would say that these systems are not easy to simulate with TDVT,
No, sure.
because entanglement is very fast, but you can do it, but somehow they're not easy to simulate. So one anyhow is restricted to few hundreds of spins.
Absolutely, absolutely. Yeah.
If one is extremely good in coding. But on the other hand, as you point out, alpha equals to 0, you can do thousands. So it's clearly that there must be somehow, a way to interpolate between the two. And this is, we are working in a very similar direction to find some method to exploit this quasi-conservation, to see whether they are reflected in the structure of the Hilbert space and to use it to do dynamics. And it seems our expectation is that for at least alpha smaller than 1, one might be able also to go to much higher spin systems, also to perform exact diagonalization and also study all the spectrum and things like this. But this somehow follows, probably I didn't put it here, but sorry. There has to be a critical alpha, because you see here it scales, this scales like 1 minus alpha. So when alpha is equal to 1, the spin waves are not conserved anymore. So there must be an n as a function of alpha, such that one can simulate many of them, and one can. It will be more clear soon, but there are methods to exploit these ideas such that one can simulate much bigger systems.
Cool, very interesting. All right. So let's see if we have any other questions. All right, I don't think we do. So thank you, Silvia, again for the talk. It was really nice. And thank you everyone for tuning in and listening to the talk. I'll just make the quick announcement that next week we have another lecture, this time by Charlie Nation from University of Sussex. He'll be talking about thermalization dynamics and the emergence of Brown-M motion in chaotic quantum systems. That's next Thursday, July 2nd. So with that, thank you again, and we'll see you next week.
Bye. Thank you.